Time for 9.3 day 2. We got ourselves some DeMoivre's theorem here. I do apologize for the choppiness of the last video. You know, public space. Hey, sometimes, you got people coming in and out. But hopefully this one will be a little bit more uninterrupted. Less interrupted, more uninterrupted. Does that work? Okay, moving on. All right, so a little warm up here. First off, let's graph z equals negative 4i. Okay, so negative 4i, that's going to be negative on the imaginary. So we're going to, boom, pop down here. I love it. Fantastic, right? Cool stuff. Wonderful. Fantastic. That's a 270-degree rotation right there. If we were thinking about conversions and things like that. My mind's always spinning. Okay, let's convert this to polar form. It's like I knew that we needed that. It's like I knew it. Okay? So let's convert it to polar form. Well, my r in this case is 4, right? So we're going to have z equals, let's just remember, r cis theta. So that's going to be 4 cis, and that was 270. Beautiful. Again, if you need to type it in expanded, that'd be cosine 270, and then plus 4 sine 270 I, or I sine 270. You can put the I here. You can put the I over here. All right. Lovely, lovely, fantastic, wonderful. I love it. Cool. I, once again, prefer that one, and most others would as well. So we know how to add, subtract, multiply, and divide complex numbers, right? And we've seen that multiplying and dividing in the in polar form is rather advantageous, right? Now, DeMoivre's theorem gives a general rule for raising a complex number to a power. However, raising when it's in rectangular form is rather messy, not that great. It's actually far more beneficial to go in polar form. Okay, so let's try one in polar form here, shall we? Because we know doing this, I'd have to write it out 3 plus 5i times 3 plus 5i, so on and so forth, over and over and over again. All right, doing that 3 times is kind of annoying. And then 4 and 5, oh gosh, no. I don't know why I started, changing my voice. Anyways. So here, you could think about this as like 4 cis 15 times 4 cis 15. And just use what we know about multiplication division, right? Multiplication in this case. All right, we take a problem that we don't know how to do yet, but apply something that we do know how to do. So that'd be 4 times 4 is 16 cis, and then 15 plus 15 is 30, right? So there we go. That's polar form. Now, if I wanted rectangular form, I'd have to draw, I would like to draw it out, 30. This is 16, so that'd make this guy 8 root 3. So we've got 8 root 3 plus 8i. Cool. That's my rectangular form, if it asked for it in rectangular. Got polar, I got rectangular, wonderful. So now, DeMoivre's theorem, we're gonna prove this, and we're gonna try and generalize this, right? Because if you actually look at it, 4 squared is 16. 15 times 2 is 30. So I'm looking at this and I'm like, well, maybe there's some kind of a pattern here that we could see here. So let's generalize this here after we go through the first couple. So for this one, I would have r cis theta times r cis theta. So that'd be r times r, which is r squared, and then cis theta plus theta. So that's, and I'll make that actually r times r for now. So now I'd have r squared cis 2 theta. Okay, cool. So will that happen again with a third power? Let's find out. So I've got them written all out. So that's r times r times r. Then cis, and then theta plus theta from what I know about multiplication, right? So that's r cubed cis theta, 3 theta. Okay, so it holds true once again, and that is going to hold true here as well. In general, what we can say is that r to the nth power cis n theta. Okay? Wonderful, fantastic, awesome. That's not no in there. That's r to the nth power cis n times theta. Cool. Lovely. Wonderful. Awesome. Fantastic. But here's the thing is, what if we're given rectangular form, we're asked to give our answer rectangular form, what do we have to do? Perhaps we can convert to polar form so we can work with this thing here and then convert back, and that's just what we're going to do here today. And as a nice little formal way of writing out like we do in textbooks, a nice little screenshot there for you. And we'll leave that up partially for this first example. So just what I was talking about, we are given rectangular form. Well, how about I convert? Let's see what the inside would be here. We'd have root 3, positive root 3, and then down 1. So we're looking like this. There we go. So that's a 30-degree reference there, negative 30 for our angle of rotation, but a 30-degree reference. So my polar form of this, my radius is 2. So we'll convert to polar. And now I have, let's see here, 2 for my radius, cis, and then either I can go negative 30 or I can go positive, 330. It's up to you. I'm going to keep it negative 330, and here's why. When I start dealing with multiplication and stuff like that, multiplying 330 by 4 and multiplying negative 30 by 4, those are two. One's a little bit easier than the other, right? Okay. So now I have the polar form of what's on the inside, all raised to the 4th power, and now I can use DeMoivre's theorem. So 2 to the 4th power, cis, and then 4 times negative 30. So I've got 16 cis, and that's negative 120. Lovely. So that's in polar form, right? Now I'm going to convert back to rectangular. Look at that sideways writing there. Okay. So to convert back to rectangular, we could go the picture route. We could go algebraic route. I'm gonna go the algebraic route here. Change it up a little bit. We could do 16 cosine of negative 120 plus 16 sine of negative 120 I. And I could draw this picture, or cosine of negative 120. What is that? So this is gonna be 16. And then that'll be what, negative 1/2, right? That's in the 3rd quadrant. That's a reference of 60. So yeah, it's negative 1/2. And then 16 and then sine of negative 120, that's going to be negative root 3 over 2. And then we got I. So I have negative 8 and then minus, let's see, that'd be 8 root 3 I. And there's my wonderful rectangular form. So again, I know we've been doing a lot of pictures, but you can also still just expand it and evaluate it with what you know about trig, okay? It's not like we should just be set in one particular way, because in certain problems, like when they're not nice trig values and we need to use our calculator, we do expand it and evaluate each one. So we can do the same here, even with our nice trig values. All right, so we want to find the following and graph on the complex plane for z to the first, z to the second, so on and so forth. We got z to the first. So what I'm thinking we'll want to do, since we're going to be raising these to powers, we're going to want to convert to polar. Okay? So let's do that. And what we're going to have is, if I were to draw this out, it'd be 2 and 2, which would be 2 root 2, because this is a 45, 45, 90, which answers another question, 45, right? Okay. So now my polar form of this is going to be, so z to the first is going to be 2 root 2 cis 45. Okay, so that's super helpful here when we move forward. So z squared 2 root 2 cis 45 squared, and then that's going to give me, well, 2 root 2 squared. 2 squared is 4. Root 2 squared is root 4, which is 2, so that gives me 8. All right, you got to be very careful with your radicals. And then I have cis. 45 times 2 is 90. And I know let's see here. I'm going to evaluate this. This would be 8 cosine of 90 plus 8 sine of 90 I. Cosine of 90 is just 0, right? And then sine of 90 is 1, so we get 8I. Okay, cool. So that's z squared. Now I'm going to do z cubed, and then I'm going to start. Actually, I'll use a different color here. Start changing it up. So z cubed, and I'm gonna pause and write this out because this is gonna get kind of monotonous. So for z to the third, I get 2 root 2 still, cis 45 in the parentheses, raised to the third. 2 root 2 to the third power is 16 root 2. And then we've got cis 135. Now I'm going to do the same for z to the fourth and to the fifth power here, and then we'll graph them all. All right, so here we go. I was able to actually change the color of that first one. So they're all different colors now. So for the first one here, z1, I'm going to, z to the first, not z1. I'm going to go ahead and graph it. So that would be z to the first. Now, z squared is 8i, so that's just straight up on that imaginary axis. And then z to the third. Well, z to the third, that's at a 135-degree angle with a radius of 16 root 2. So I really actually don't even need to convert these when you really think about it to graph them, because 8 cis 90, that would just be 8 with an angle of rotation of 90, right? And now 135, look at that. We're going, baby. We're going. And then, man, this is gonna get crazy. This is gonna get huge. I got to go over this way. We're going 16 root 2, so even longer yet. And then perhaps I went too crazy. Perhaps I went too large with the scaling here. And then we've got even larger yet. So we went from 2 root 2 to 8 to 16 root 2 to 64, and then all the way to 128 root 2. Woo! I like that. Yeah, I think I misspoke on this one. I think I said like 16 root 2. My bad. But look at that. That's kind of fun. All kind of like spirals. And oh my goodness, look at that. Us mathematicians always love finding cool designs and things, especially those spirals. You see how like math books got all those fun spirals, right? Well, there you go. All right. So very, very powerful theorem here from Mr. DeMoivre himself. Real nice guy for putting that together for us. Very, very helpful to convert to polar form, evaluate it, and then convert back to rectangular if necessary. But that conversion is going to save you a ton of time. Maybe not when you're just squaring it, but when you're cubing it and raising to the fourth and to the fifth, oh my goodness, a huge time saver. Shorter lesson there. Yeah, we're done. That's it. That's bueno. That's awesome. Fantastic. Have a wonderful day, guys. America Freedom, rock and roll, Costco, Riverdog Jenny, on the gram. Deuces.